Hello, and welcome to the next edition of Organic Chemistry 1. I'm going to share my screen. Okay, we'll start up with a review of electronegativity and bond polarity. Right, so a nonpolar covalent bond occurs when there's little or no difference in electronegativity between the atoms that are bonded to each other. A polar covalent bond is one in which there's a dipole moment, a separation of charges. In this case, with carbon and chlorine, the bond is polarized toward the chlorine. When the difference in electronegativity is so great that there is a complete transfer of an electron, then we have two fully charged particles, and then we have an ionic bond. Okay, here's chloromethane, and chloromethane is polarized toward the chlorine. We can see that from the electron paramagnetic map that red indicates a high electron density. On the other side of the molecule, we have a low electron density. Okay, here is an abbreviated table of Pauling electronegativities. Fluorine is the most electronegative element, followed by oxygen, and then nitrogen and chlorine. Then over on the left side of the periodic table, we have those with very little tendency to attract and hold electrons. Okay, to determine formal charges on an atom, what we can do is take the group number, or the number of valence electrons, which also corresponds to the position of the atom in the row, the element in the row. We subtract the non-bonding electrons, not the non-bonding pairs, but the number of non-bonding electrons, and then 1/2 of the shared electrons. Another way of stating this would be just to say the number of bonds. Right, so oxygen in the hydronium ion, oxygen is in group 6. We subtract the 2 non-bonding electrons, and then we subtract 3 bonds, which gives us a charge of +1. For the NO plus ion, for oxygen, we subtract 2 for the number of unshared electrons, and then 3 for the number of bonds, and that gives us a charge of +1. For nitrogen, nitrogen has 3 bonds and 1 unshared pair, so 5 minus 2 minus 3 would be 0. The individual charges on the atoms have to add up to the overall charge on the ion. Or if the molecule is 0, they have to add up to 0. Okay, here's a addition product of ammonia and borane. Okay, we can do the same thing. Nitrogen has 4 bonds. Okay, so it's in group 5. There are 0 unshared electrons minus 4 bonds, so that gives us a charge of +1. Boron is in group 3. It has no unshared electrons, and it has 4 bonds. 3 minus 4 is -1. Okay, and there's no overall charge on this species. Okay, this is pretty close to where we left off last time. One of the things we can look at is to notice common bonding patterns. Okay, for neutral atoms, boron will have 3 bonds and no lone pairs. Carbon will have 4 bonds. Nitrogen has 3 bonding and 1 non-bonding. Oxygen has 2 bonding and 2 non-bonding. And halogens like chlorine would have 1 bonding and 3 non-bonding. Okay, there are no familiar examples of a positively charged boron, but a negatively charged boron would have 4 bonds. Okay, positively charged carbon, you can see, looks very similar to a neutral boron. 3 bonds, 6 valence electrons, but no octet. A positively charged nitrogen, okay, think about the ammonium ion, NH4+, okay, has 4 bonds, so it resembles the carbon that's diagonal to it, and carbon resembles the boron with a negative charge, which is diagonal to it. Then we go to nitrogen. Oh, let's go back to carbon. If we convert one of these bonding pairs to a non-bonding pair, then we acquire a negative charge. Okay, this is called a carbanion, and it does have an octet. Okay, if we go back to nitrogen, the ammonium ion is a familiar example, but if we go the other direction, we convert a bonding pair to a non-bonding pair. Nitrogen with 2 bonds and 2 unshared pairs would have a negative charge. All right, oxygen. A neutral oxygen has 2 bonds and 2 unshared pairs. Okay, familiar example would be water. If it has 3 bonds and 1 unshared pair, then oxygen has a plus charge. That would be like hydronium ion. And if it has 1 bond and 3 unshared pairs, oxygen has a negative charge. Okay, an example would be the hydroxide ion. Okay, for chlorine, chlorine forms 1 bond. We'll see some reactive intermediates where it forms 2, and in that case, it will have a plus charge. When chlorine has a negative charge, it has no bonds. It's a separate ion. It's a chloride ion. Resonance structures represent delocalization of electrons. Not every molecule will exhibit resonance structures. You have to have groups that can push electrons, and you also have to have groups that can accept electrons. Okay, so there are some species, some molecules or ions that are not adequately represented by a single Lewis structure. Okay, this is one example. Okay, we can push a pair of electrons from the nitrogen to the carbon. That makes this a double bond, and that gives nitrogen a plus charge. Okay, we can't gain or lose any electrons. Charge must be conserved. We have to have the same total charge in all of our resonance contributing forms. Okay, these are separated by a double-headed arrow. Okay, that's distinctly different from, here we go. That's distinctly different from this, which represents an equilibrium or a reversible reaction. Okay, in an equilibrium, we can move atoms around, but in a resonance situation, we can only move electrons. Okay, so that means that this CN bond has some partial single bond and some partial double bond character. And the plus charge is delocalized on both the carbon and the nitrogen. Okay, since these are not equivalent resonance structures, they don't contribute equivalently or the same to the overall structure. Okay, so resonance forms can be compared using the following criteria, beginning with the most important. Okay, so we want a structure that has as many octets as possible. Let's go back to this example. Okay, in the structure on the left, carbon does not have an octet. In the structure on the right, everyone has an octet. So this would actually contribute more than the one in which there's no octet on carbon. Okay, so the actual structure is closer to this one, but this does contribute some to the overall structure. Has as many bonds as possible. Has the negative charge on the most electronegative atom. Okay, so we'll see some examples of that. In fact, I'll draw an example. Okay, those of you that took Chem 2 over the summer, okay, we did an equilibrium experiment in lab with iron thiocyanate. Sulfur has 6 valence electrons, carbon has 4, nitrogen has 5. And this is a negative charge. So we add 1 for the ion. Okay, so that adds up to 16 electrons. Sulfur is in the same family as oxygen. Okay, so we start out by connecting these with single bonds. Fill out the octets on the outer atoms. Okay, the problem here is that carbon doesn't have an octet. In fact, it doesn't even have anything close to an octet. It's only got 4 valence electrons. Right, so let's move this pair over here. I can't add or subtract any, I can just move them. This one over here, carbon now has 6. And if I move this pair over here, okay, now everyone has an octet. Right, carbon normally forms 4 bonds, so it would not have a charge. Sulfur is in the same family as oxygen. The water molecule has 2 bonds and 2 unshared pairs, so sulfur would have no charge. Nitrogen is in group 5. Okay, we subtract the 4 non-bonding electrons, and then we subtract the 2 bonds. Okay, so 5 minus 6 is minus 1. Okay, so nitrogen carries a minus 1 charge. All right, the other resonance structure would be this one. And the way I get there, if I start by pushing from the negative charge this way, okay, that's going to give carbon too many bonds, so carbon has to push a pair of electrons onto the sulfur. Right, so sulfur would have 3 unshared pairs. This would be a single bond because this bond moved over here. And nitrogen would have a triple bond to carbon. Okay, so this is 3 non-bonding pairs, 1 bonding pair. That would be like hydroxide, oxygen and hydroxide. So here sulfur carries the plus charge. Okay, so the major contributor by rule number 3 would be the one in which the negative charge is on the more electronegative element. Nitrogen is more electronegative than sulfur. Okay, so that means that, for example, the CN bond has more double bond character than it has triple bond character. It would be somewhere in between, but it's closer to the double bond. And this would be closer to a double bond than a single bond. Okay, by closer to a double bond, okay, what I mean is that a double bond is, for example, measurably shorter than a single bond. Okay, and we want to have as little charge separation as possible. Okay, so here we have some major and minor contributors. Okay, this is formaldehyde, and in this case, there's no charge separation. Okay, if we move a pair of electrons onto the oxygen, okay, that gives oxygen 3 unshared pairs, a negative charge, and then carbon has a plus charge. Okay, another way to look at that is that the electrons moved away from carbon. It was neutral, now it's positive. They moved toward the oxygen, so it becomes negative. All right, this is a minor contributor because carbon doesn't have an octet and there is more charge separation. Okay, it does contribute enough to make this CO bond more polar though. All right, here is the cyanate ion, okay, very similar to the thiocyanate that we just showed. And here, the negative charge is on the oxygen. So that would be the major contributor. Okay, here are some other non-equivalent resonance structures. Okay, this would be methyl nitrite. And if we move a pair of electrons toward the nitrogen, from the oxygen toward the nitrogen, and then move another pair onto the oxygen. Okay, here we have charge separation. So this would be a minor contributor, and this is a major contributor without the charge separation. Okay, this is a similar example. A major contributor in this case would have octets on all of the atoms. Okay, this one on the left lacks an octet for carbon. Okay, here's another example. Right, we have a negative charge on the carbon. Okay, everyone still has an octet. But if we move from the lone pair of electrons toward this carbon, then we have to push a pair up onto the oxygen. Okay, the major contributor is the one with the negative charge on the oxygen, because oxygen is being more electronegative, is better able to carry that negative charge. Okay, here's the acetate ion. Okay, when acetic acid loses a proton, it becomes the acetate ion. Okay, in this case, we have 2 equivalent resonance forms. Okay, and each one has a bond order, each CO bond has a bond order of 1.5. Right, next we're going to look at formula representations. Right, here is the molecule ethane. Okay, it's not too difficult to draw out the full Lewis structure of ethane. But we're going to encounter larger and larger molecules, and it will become very tedious to draw every single bond. Okay, there are some other representations which still preserve the structural meaning. This is what's called a condensed formula. Okay, we write this as CH3, CH3, even though the hydrogens are actually not between the carbons. Okay, that's understood. Okay, if we have two or more identical groups, then we can use parentheses and a subscript to represent them. Okay, and an example. Actually, let's back up here. Before we get to the parentheses. Okay, here is the full Lewis structure. Okay, sometimes the lone pairs on certain atoms are implied, so bromine would have 3 lone pairs. Okay, this is the condensed formula. Even though the hydrogens are not between the carbons, that's understood. Okay, here's another example of Lewis structure versus a condensed formula. Okay, we just saw ethane. This is a compound called isobutane, and this is a condensed representation. Carbon has 3 of the CH3s. These are called methyl groups attached to it, and a CH. Okay, in a linear structure like this, we have CH3, and then CH2 repeats itself 4 times, and then we have a CH3 on the end. Okay, the molecular formula in most cases does not give adequate information about the structure. Okay, for example, the molecular formula for N-hexane would be C6H14, but it turns out that there are other compounds that could have that molecular formula. Okay, but this tells us, this actually preserves the structural information. Okay, here are some other Lewis structures versus condensed formulas. Okay, this one is diethyl ether. Okay, sometimes we show the bonds between carbon and oxygen. Sometimes we don't. Okay, either one is acceptable. We could also show this as O with 2 of these CH3, CH2 groups attached to it. We do need to show the H that's on the oxygen here. This is ethanol. This is isopropyl alcohol. We could show this as 2 methyls in parentheses, a CH and an OH, or we could show it as CH3, CHOH, and CH3. And this is dimethylamine. Okay, we could show both the CH3s, or we could show the CH3s in parentheses with a subscript 2. Okay, since a subscript and parentheses indicates the number of times that we repeat, we have this. Okay, so we repeat Na twice, we repeat it once, and this is bananas. Okay, double bonds and triple bonds have to be shown explicitly. Sometimes they are implied, in this case, CN. For acetaldehyde, I prefer the notation on the right rather than CHO. Same way with acetone and acetic acid, I prefer to show the CO double bond rather than COOH. This implies that the oxygens are connected to each other, and you can see that they are not. This implies that the oxygen is between the two carbons, but of course it's not. Right, we can simplify even further using something called line angle drawings. And what we do here is we write out the formula, and bonds are represented by lines. Carbons are present where the line begins and ends, and where two lines meet. Okay, we omit the hydrogens, they're implied. Nitrogen, oxygen, and halogens must be shown, and if there are H's on the nitrogen or the oxygen, those also have to be shown. Okay, we have to show any double or triple bonds. Okay, because of the tetrahedral shape of carbon, okay, this structure is actually not a straight line, but it's a zigzag. So we omit the hydrogens, and each one of these line segments represents a carbon-carbon bond. Okay, since we know that carbon forms 4 bonds, the hydrogens are implied. Okay, this one on the end, this carbon on the end, since it has 1 bond shown, we assume that the other 3 are to hydrogen. Okay, these 2 in the middle, this one, for example, since there's 2 bonds shown, we assume that the other 2 bonds are to hydrogens. Okay, here's another example of a line angle drawing. The oxygen and the double bond to oxygen must be shown. Also, this hydrogen, which is a critical part of what we call this the functional group, and we'll talk about functional groups shortly. That also needs to be shown. Okay, so here are some other examples of line angle formulas and condensed structures. Okay, here is hexane. Okay, it has 1, 2, 3, 4, 5, 6 carbons. Okay, here's one with a double bond. Okay, on the second carbon here, there are 3 bonds shown, two to the from the second to the third carbon, and then 1 between the second and the first. Okay, so since carbon forms 4 bonds and 3 are shown, we assume that the 4th one is to a hydrogen. Okay, same way with the carbon with the third carbon. And then the 4th carbon, we assume that since 2 bonds are shown, that the other 2 are to hydrogens. Okay, and that's what our condensed formula shows us, CH2. All right, oxygens must be shown, and any hydrogens that are on the oxygens also need to be shown. Okay, this carbon right here that's bonded to the oxygen, okay, 3 bonds are shown, so we assume that there's a 4th bond to a hydrogen. Okay, here are some cyclic or ring structures. Okay, this CH3 is sometimes represented as just a stick. Okay, it's understood there's a CH3 on the end here. And again, nitrogen needs to be shown explicitly. As I said, I prefer this representation, C double bond OH rather than COOH. All right, next we'll talk about, actually, let's skip over that one. I'm going to mention this briefly, and that's empirical formulas. This is the smallest ratio of elements in a compound. In the old days, they would burn an organic compound, and then they would absorb the water that was produced and the carbon dioxide that was produced in order to get percent composition. Okay, so if we're given percent composition, okay, it's so many percent carbon, so many percent hydrogen, for example, and if there's oxygen, so many percent oxygen. Okay, we assume that there's 100 grams of that compound. And then we would convert the grams of each to moles. For example, I don't know if this is a real compound or not, but let's say we had 40% carbon, 45% oxygen, and 15% hydrogen. Okay, we assume that there's 100 grams of the compound. So there would be 40 grams carbon, okay, times 12 times 1 mole for 12 grams. 40 divided by 12. Okay, would be 3.33 moles. Okay, 45 grams because we're assuming that there's 100 grams of the compound, so this is 1 mole. 16 grams. Okay, that would be 45 divided by 16, that would be 2.8. 2.81 moles. And then I think this is going to make sense, but that's so that would be 15 moles. Okay, so we look at the mole ratios, and then from that we can derive an empirical formula. Okay, probably very few instances where we would actually need to do that. We'll talk about later on in the semester in lab where we can get, or we can deduce a formula from a technique called mass spectrometry. Right, now we're going to change the subject and look at wave properties of electrons. Electrons behave as both particles and as waves. And there is a mathematical function called a wave function, which describes the size, shape, and orientation. Okay, when we do linear combinations of atomic orbitals, combining orbitals between two atoms involves bond formation. Combining orbitals on the same atom is what we call hybridization. When we make these combinations, the orbitals have to be conserved. And what that means is that, for example, in hybridization, if we hybridize 4 atomic orbitals, we need to come up with 4 hybrids. If we combine orbitals on bonds, if we combine 2 orbitals, then we need to come up with 2 molecular orbitals. Right, waves that are in phase add together and the amplitude increases. Waves that are out of phase cancel out. Okay, a good example is sound waves. Okay, if they are in phase, then they add together and we get a wave with a larger amplitude. If they're out of phase, that is where this minimum meets, or this maximum meets this minimum, like this. Okay, that would be what's called destructive interference. These waves would cancel each other out. And with sound waves, a couple of applications include noise canceling headphones. Another example is in the Bay Area around San Francisco. They have a train system called the BART, Bay Area Rapid Transit. There's some locations where the trains go underground, and then there's others where they go above ground. They have these devices that analyze the sound from an approaching train, and then they generate a sound wave which is out of phase, and this reduces the noise from the trains. We'll look at 2 main types of bonding. Sigma bonding, in which the electron density lies between the nuclei. Okay, there's a direct overlap. Sigma bond can be formed by 2 s orbitals, 2 p orbitals, or an s and a p, or by hybridized orbitals. Okay, when sigma bonding occurs, you get a bonding molecular orbital and an anti-bonding molecular orbital. This goes back to the idea of conserving orbitals. The bonding molecular orbital is lower in energy than the 2 original atomic orbitals, whereas the anti-bonding MO is higher in energy. Okay, so here we have the hydrogen molecule. And when 2 hydrogen atoms combine, their waves can interfere constructively to form a bonding molecular orbital, and that's lower in energy than the isolated 1s atomic orbitals. Okay, if it weren't lower in energy, the bond probably wouldn't form. And then the other situation would be an anti-bonding, where they destructively interfere. Okay, so here's the hydrogen molecule. Most of the electron density is between the 2 nuclei. And here is an anti-bonding molecular orbital by destructive wave interference. And we get a node or a region of almost zero probability between these electron regions. And that's designated as sigma star to indicate that it's anti-bonding. Right, so we have the two atomic orbitals at this energy, and then we have a bonding molecular orbital and an anti-bonding. There are two valence electrons in the hydrogen molecule, and so we start filling out the bottom lowest energy orbital first. And just like with atomic orbitals, molecular orbitals can hold a maximum of 2 electrons. If we had something like a hydrogen molecule anion, okay, H2 minus, okay, that third electron would have to go up here in the anti-bonding orbital. Okay, these overlap directly, and so this is a sigma overlap. Okay, with chlorine, we can have a direct head-on overlap between p orbitals like this. That's also a sigma. And then this is the anti-bonding. Well, this is actually a bonding and anti-bonding between S and P. All right, the other type of bonding that we'll look at in this course is pi bonding. And this is where p orbitals will overlap side to side. Okay, even though there's overlap in 2 places, this is considered just one bond. And then we also have an anti-bonding or pi star molecular orbital with a node between the 2 regions. Okay, this is an important comment down here. A pi bond is not as strong as most sigma bonds. Okay, that's important in predicting how molecules will react. Right, so here is ethylene. Here's the Lewis structure. There is a sigma bond between the 2 carbons, and then there's also a pi bond. So that's where we get the double bond. We have a sigma and a pi. A triple bond will consist of a sigma bond and 2 pi bonds. Bond angles cannot be adequately explained by simple S and P orbitals. The valence shell electron pair repulsion, or VSEPR, VESPR, is used to explain and predict molecular shapes of molecules. And one of the ways that we can also explain VSEPR is through something called hybridized orbitals. Hybridization is a mathematical operation in which we take the wave function, for example, describing an s orbital and that describing a p, and we combine them. If we add them together, we get an sp hybrid. Okay, since the value of the function is positive, and it's positive here, positive and a positive results in a larger positive. A positive and a negative results in a smaller lobe. Okay, these are not charges, these are the values of the sign of the function. Okay, an s orbital is positive everywhere. A p orbital has a node where the value is 0. On one side of the node it's negative, on the other side it's positive. Okay, since we're combining an s and a p, we need to generate two hybrids. So we add these and then we subtract these to get the other one. And you'll notice that these are the same, but they're oriented in different directions. And so this is used to explain molecules that have a 180-degree bond angle. I'm not so much concerned that you can derive these, but just be able to associate sp with a linear shape. Okay, beryllium hydride is, we know that experimentally to be a linear molecule. The electron configuration of beryllium is 1s2, 2s2, and there are no unpaired electrons. And so that's why we do the linear combinations to get the two sp hybrids. And this also corresponds to the correct geometry. Okay, if we combine an s and two p orbitals, we get 3 sp2s. And we have one p orbital here that we didn't hybridize. Okay, these sp2s are in a trigonal planar arrangement. And a good example here is borane, BH3. It's trigonal planar. And each one of the sp2 orbitals is forming a sigma bond with a hydrogen. If we combine an s orbital with 3 p orbitals, we get 4 sp3s, and they are in a tetrahedral arrangement. Okay, so this is what we have in something like methane. By VSEPR, the best way for 4 electron-rich groups to avoid each other is a tetrahedral arrangement. Methane were flat, the bond angles would only be 90 degrees. Okay. All right, so this is what I'm most concerned about, not that you can necessarily derive these hybrid orbitals, but whenever I talk about sp, okay, associate that with a linear geometry. sp2, associate that with a trigonal geometry, and sp3, associate that with a tetrahedral. Okay, so in ammonia, since nitrogen has a tetrahedral electron pair geometry, okay, it must be sp3. The reason that, in contrast to methane, okay, which has 109.5 degree bond angles, the reason that the HNH bond angle is smaller is that this lone pair takes up a lot of room, and that causes these this bond angle to compress a little bit. Okay, with water, you have 2 lone pairs, and the HOH bond angle is about 104.5, so it's compressed even further. So ethylene has 1 sigma and 1 pi bond. The carbons and the hydrogens are in a trigonal planar geometry. And so these are sp2 orbitals, and then there were 3 p orbitals originally. We hybridized 2, and then we have 1 left over, and this forms a pi bond, side-to-side overlap. In the case of acetylene, where we have a triple bond, the hybridization of the carbons is sp. Okay, so that means that there were 2 p orbitals which were not hybridized, the py and the pz. They're perpendicular to each other, and they form 2 pi bonds. And then we also have a sigma bond between the sp orbitals. Okay, sigma bonds can rotate freely, whereas pi bonds don't. You actually have to break the bond before you can rotate about this carbon. Okay, I'm going to go ahead and stop there. And end the meeting.